Okay, good morning everyone. I posted a homework. Okay, please start work on it early. It's due, I think, next week Sunday, depending on how far we get along. I think hopefully after today's class, you should be able to solve all the problems in the homework, or at least give it a good crack. Okay. We're going to continue forth with the Frenet-Serret frame, and I'm going to solve a problem today, which is quite close to what you have in your home. Okay? Frenet-Serret frame. I just want to list the first three results that we have from last time. So ET is a unit vector along the tangential direction. This is given to us as dr by ds, where r is the position vector of the particle at some instant in time. S is the distance along the path. Again, you're going to see all these exercises today. Then kappa, En, kappa being the curvature. This is det by ds. These are the Frenet-Serret definitions. And the last one is the cross product of Et, and En defines the third unit vector in the frame. So that B Et cross. Okay, so these are the three formulas that we saw. We saw a couple more, which we will see today as well. So I want to start off with the problem. That's the problem. As I mentioned last class, the use of the Frenet-Serret frame is more so when the path of the particle is already defined for us. Okay? So let's consider a bead on a parabolic wire. Okay, so this is some kind of a parabolic trajectory, and a bead is sitting on it. Okay, at this point in time, we will ignore the effect of friction. It is not a big deal, we can always include friction. Okay, so at this point in time, let's say that smooth, frictionless. And I'm going to set up a coordinate frame. Starting here, x-axis, y-axis, z-axis coming out of the page. And we are considering a planar problem. Okay, so this is not a two-dimensional problem yet. The equation of this parabolic wire is the following. Y is minus x squared. And here are the things that we want to do. We want to employ the Frenet-Serret frame, obtain the equation of motion. For the bead, this is the bead of mass m. So this is treated as a particle on a wire. Okay, it's not yet a rigid body. And then I also want to obtain certain conditions on the initial velocity of the bead. That is, I'm taking this bead, giving it an initial velocity and initial displacement. That's how this bead is traveling along the wire. There are no external forces besides gravity. I want to see, okay, given an initial displacement, what should be the limit on the initial velocity so that the bead does not jump off the parabolic track. There is a possibility that if I give this bead a very high initial velocity, it will not even travel along the track, it will just fly off the track. So I want to see what these constraints are. Okay, can we come up with an equation? So what is the constraint? On the initial velocity that the bead does not lose contact with the wire. So the loss of contact does not happen. Okay. So this is a planar problem. And as you know, bodies can be put into motion either by means of external forces or by means of initial conditions. In this situation, there are no external forces other than gravity. There are constraint forces. The normal force between the bead and the wire is a constraint force. So, but besides that, there are no other external forces. So the bead is set into motion due to initial conditions. Okay. And since this is a planar problem, the curve that we are looking at is a planar curve. And based upon the choice of our coordinate system, I can call this curve as y as a function of x. So this is y is f of x, where f of x is minus x squared for our situation. In your homework, it's going to be a cubic trajectory, so that's going to be f of x is x cubed, or it could be an elliptical path, it could be a circular path, it could be whatever it is. Okay? So for us, f of x is minus x squared. But when I develop the equations, I'm not going to substitute minus x squared because I want to develop something in a very general situation so that you can employ it for any kind of a path that is given to you. Okay? Alright. So to start off, let us set up some unit vectors and so on. So this is the k, this is j, and I hat. Okay. And since it is a planar problem, I can assume that this bead or this path that I am showing is for a constant z value. Does this make sense to everyone? Okay, so I can say that z is equal to z naught for this particular plane. Okay, so this is z is equal to z naught plane. So that's a constant value. The z value does not change. The only values that change are x and y. So what are the constraints on the problem? What are the configuration coordinates? What are the number of degrees of freedom? Okay. So constraints, configuration coordinates. It's a particle. In the most generic sense, it's going to have three configuration coordinates, one along the x, one along the y, one along the z. Okay. So this is going to be some x, y, and z. What are the constraints? Planar problem. That's the first constraint. So z is equal to z naught. What is the other constraint in this problem? Yes, yes. You can just say, tell me that.
It's constrained to the wire.
It's constrained to travel along the wire, so the path of the problem is already known to me, path of the body is already known to me, so y is f of x, which is in our case minus x. Right? So these are the constraints, three configuration coordinates, two constraints, the number of degrees of freedom is 1. This number of configuration coordinates, which is a total of 1. The best variable that that will act as a degree of freedom. Any takes on that? What could I, yes?
Let's go with the x position, because if you know x, you know y.
Absolutely. If you know x, you know y. If you know x and y, then you know you're on a constant plane anyways. So x of t could be a reasonable choice for the degree of freedom. So this is going to be x of t, which means that I expect the equations of motion to be in terms of x of t. So equations of motion is equal to 1. The number of equations of motion is the number of degrees of freedom. The number of equations of motion is equal to the number of degrees of freedom. So we expect a second order ordinary differential equation in x of t. We expect second order ODE in x. Okay. Any questions so far? Everything reasonable? Okay. Let's proceed further and see if there are any questions. I'm going to also label another character here, which is the path variable, or the distance traveled along the path. I'm going to call it as S of t. Okay. So for me, distance traveled along the path is S of t. Traveled along the path. Okay. Which is where you're getting your character ds and so on. So ds is an infinitesimal distance traveled along the path. dr is the displacement vector, or an infinitesimal vector joining the position of a point at time t and time t plus dt. Okay, those are the two things that you typically see. Alright, so I'll set up the basic problem here, and we'll write out its position vector. And I'm going to do some stuff that is very common to Frenet-Serret frames. If you are using Frenet-Serret frames to solve a problem, you'll be doing all of these things. So you don't need to repeat everything in your homework assignment. You can just take these from what I do in the lecture. Okay? Once again, why are we using the Frenet-Serret frame? Is because it is the most efficient way to solve a problem whose trajectory is already known to us. That is the only reason. I can solve this problem, you can solve this problem using any kind of a coordinate system. No harm done. Okay? It is just that this makes it a little more easy. Alright, so set up the problem here. X-axis, y-axis, unit vector, and k hat. This is the particle. I'm going to draw a position vector from a fixed observer. So this is the frame F1. It's a fixed frame or an inertial frame. Okay. This is the origin O, particle P. This is y is a function of f of x, and z is equal to z naught. And so if I write a position vector from the point O to the point P, this is obviously not tangent to the path. This is just a position vector starting from the point O to the point P. So R P slash O, I'm going to use the Cartesian frame to write the position vector. It is going to be x of t in the I direction, some y of t in the j direction, and the z of t. Okay. once you have written this, you start substituting everything that you know about y of t and z of t. Z is a constant, y is already known as a function of your time, of your variable x. So this tells me r of p slash o is x of t, can't do much about it. Then instead of y of t, I'm going to write it as f of x. J hat, and then z naught k. And obviously, at any instant in time, the tangential vector is going to be tangent to the particle path at that particular point. Okay, so in this case, the tangent vector is going to be ET. Okay. And what you typically would want to do in most problems is you would like to come up with a relationship, a general relationship for a planar curve between the unit vectors of the tangential normal system or the Frenet-Serret frame and the Cartesian system. So this is generic. Okay, so for planar curve, it is typically useful to relate the two coordinate vectors. Okay. We will try to relate. En, B with the ijk system. ET and EB is a fixed frame. Sorry, it's a moving frame. Okay, it's traveling along with the particle. ijk is a fixed frame. When we apply Newton's laws, we would like to have everything with respect to the fixed or the inertial frame, which is why we are going through all these hoops, right? Okay. So let's start off with this equation here. Okay. So ET, and this is something you will have to do in your homework problems, or if you choose to use this technique in the future for any problem, this is something you will have to do. Okay, you have to converse between these two coordinate systems. What's the transformation equations? That's what we're looking at. So ET by definition is dr by ds, which I'm going to use the chain rule and convert it into the following. This is dr by dt, dt by ds. Or I can say this is dr by dt divided by ds by dt. I'm just taking this entire term, bringing it from down to the denominator. Okay. And by definition, what is this going to be? So the dr is et times ds, right? So ds times dt. So if I take this unit vector and take the dot product of it with itself, what should it give me? It should give me the square of its magnitude. Does this make sense to you? Okay, because et is a unit vector. So et dotted with et is 1. So I'm left with ds times ds. So if I just expand this, so this is an aside. Ds square. Okay. So keep that in mind. And so essentially what we have here is the following. So this is dr by dt divided by square root of a dot product dr by dt dotted with dr by dt, which is ds by dt whole square, which is going to be ds by dt square root of. So this is a dot product. So I need to evaluate each of these terms, which means I need to evaluate dr by dt, which we will do very carefully. This is all generic for all planar curves. So dr by dt is, a few manipulations have to be done now. So this is d by dt of that entire quantity. That is x of t I hat, f of x j hat, z naught k hat. We already know that I, j and k are unit vectors of a fixed frame, which means that if I take the time derivative of those unit vectors, they will end up giving me 0. Okay, so that's a matter of fact. I guess I don't want to, maybe can I write here if everybody can see the back? Right here? I guess it's not. But all I wanted to say was, if I differentiate I, j, k, it's going to be 0 with respect to time. I think it's quite obvious. So then I differentiate x of t, so that gives me x dot. X dot I hat. Then I have to differentiate f of x with respect to time, which means I have to employ the chain rule there, and maybe I can sneak through and write it here somewhere. Maybe I'll write it on the other panel. D by dt of f of x, use the chain rule. So this is going to be d by dx of f of x dx by dt. Dx by dt is x dot. Df by dx, if we have spatial derivatives, I'm going to put a prime on it. 1 prime is one spatial derivative, 2 primes means two spatial derivatives. So this we are going to write as df by dx times x dot or f prime x dot. Okay, so which means if I go back to dr by dt, this is going to be f prime x dot j hat. Am I making sense to everybody? Z naught is a constant, k does not change with time, so the last term does not appear in my differentiation in the system. So dr by dt watch this. X dot is a common factor, so pull that creature out. Right? So this is going to be x dot I hat f prime dot product of dr by dt with its. And you see why I did not use the Frenet-Serret frame to write the position vector is because I don't know what the rate of rotation of this frame is to begin with. It's not very obvious to me as to what it is. Though it does not mean that we cannot write it that way. Okay? So dr by dt dotted with dr by dt is x dot I hat f prime j hat dotted with x dot I hat f prime j hat. So this is the dot product of two vectors, which gives you a scalar. dr dot with dt, dr by dt dot with itself is ds by dt square. X dot and X dot is X dot square. Then dot product of vectors, take the common vectors, take their dot product. So I dot is 1. F prime j dot dotted with F prime j dot is F prime square. So this is 1 plus F prime square. Making sense to everybody? I dot dotted with I dot is 1. F prime times j dot j hat dotted with F prime times j hat is F prime square. Take the square root on both sides. So I have ds by dt is x dot 1 plus F prime square all to the power 1 by 2. And I'm going to collect all these results right here. And ds by dt is s dot. Okay, so s dot ds by dt is what's the full one? So that's one thing. I can differentiate it one more time and do other things as needed on a need to do basis. Dr by dt r dot. Okay, and this is x dot I hat F prime. So these are all the results column where we're going to collect all these like-minded terms, and F prime is d of x by dx. Okay, any questions, please? Pace of writing is okay with everybody? You may not see where we are going yet. What I am trying to do is I am writing this as a generic derivation for all planar curves. My aim at this point in time, before even solving this problem, is to try and relate for a planar curve, f of x, y is equal to f of x, what is the relationship between the Frenet-Serret triad and the ij cases. Once we have this generic equation derived, then we can start using it on our problem. Okay. So take all these results, plug them back into the ET. So ET is dr by dt by ds by dt. dr by dt is known, ds by dt is known, substitute. This is x dot I hat f prime j hat by ds by dt, which is x dot 1 plus f prime square to the power 1. X dot cancel off. So this is our first result, which is a relationship between the tangential unit vector and the unit vectors of the Cartesian system for a planar curve. If I take a three-dimensional curve, the process is going to be the same. The results will look slightly different. Okay, so I'm going to collect that result here as well. With your permission, I'm going to get rid of this guy. X dot is cancelled off, so ET is I hat f prime j hat by one plus f prime whole to the power 1. be ready for the next one. Okay. That's going to be much more of a beast than this one. But we have to do it once. Okay, many of these things you'll see in this course, you just have to do it once so that you can employ the results in solving useful and elegant problems. So then I need to look at the next one. So this is a relationship between the tangential and the unit vectors of the Cartesian system for a planar curve. Do it for the normal coordinate. So by definition, kappa En is dEt by ds. This is the second Frenet-Serret formula. Chain rule. This is dEt by dt times dt by ds. Or dEt by dt by ds by. Already have ds by dt, so that's good news. The only painful thing here is I need to take et and then take the time derivative of this nasty thing. Okay, which we will do step by step. So we have this guy. What is that? So dEt by dt is d by dt of this term here, this big chunk here. D by dt of I hat f prime j hat 1 plus f prime square to the power 1 by 2. I am making use of the product rule in differentiation. So essentially, I'm going to first differentiate the numerator, keep the denominator fixed. Then I'm going to differentiate the inverse of the denominator. So I'm going to differentiate 1 by 1 plus f prime square while keeping the numerator fixed. Okay? This is going to be quite painful, but we'll do it. So first situation, I keep this fixed. So this is going to be 1 by 1 plus f prime square to the power 1 by 2 d by dt of that term. Plus I hat f prime j hat d by dt of 1 by the power 1. So term by term, d dt by dt, the first term 1 by 1 plus f prime square to the power 1 by 2 remains there. 1 by d by dt of I hat 0. So that's going to be 0. Then I'm going to have d by dt of f prime. Is write this here, hopefully everybody can see. D by dt of f prime, I'm going to use the chain rule. So first the differentiation with respect to x and then differentiation of the x itself. So this is essentially d by dx of f prime dx by dt. Dx by dt is x dot. Df prime by dx is the second derivative of f with respect to x, so f double prime. This is f double prime x dot. So this is 0 vector, and then f double prime x dot make sense to everybody? Right? Chain rule, that's all I'm doing here, multiple times. Plus, the other nasty fellow is I had plus f prime j hat. With your permission, can I do this very quickly? It is just a basic differentiation. Okay. So first I differentiate all the entries inside, and then I differentiate the fraction itself. And so this is going to end up being the following. So this is minus 1 by 2. It's just an exercise in differentiation. Okay, so minus 1 by 2. 1 by 1 plus f prime square. Minus 1 by 2. Minus 1 is minus 3 by 2. So comes to the denominator is 3 by 2. And then differentiation of the contents within 1 plus f prime square, which is going to end up being differentiation of 1 with respect to time, gone. Differentiation of f prime square is dx by dt. Chain rule once again, so this is x dot, then d by dx of f prime square is first of all 2 times f prime times the differentiation of f prime with respect to x or f double prime. Is everybody clear with this one? So I actually used 2 chain rules. The first chain rule was used here. The second chain rule was used when I differentiated f prime. So I should in reality have written this as the following. d by dx of f prime square is d f prime square by d f prime d by dx of f prime. Okay, so this is where you get this guy from, and then this quantity comes from. Okay, so complete that out, and this is 2 times f prime, f double prime, x dot. Factor of 2 is gone. You'll end up getting a formula that you'll really like seeing. Yes, question.
So when you took a derivative of f prime, the bottom left you have it equal to f double prime x dot. But should there be another x dot in the top right? Since you took the derivative.
No, so this is from here.
Yeah.
So I'm taking only this quantity.
Okay.
So this is with respect to time. If I do it with respect to time, I'm going to get an x dot.
Okay.
If I do it with respect to the spatial derivative, right, then there is no mention of time here.
Okay.
And everything is combined together by adding this term at the end. Does this make sense?
Okay.
Yeah. We've already included the time by saying that this quantity, by definition, is this multiplied by that. So the time has been taken care of. All I'm doing is only spatial derivatives,
Okay.
which comes through to this way.
Okay. Gotcha.
Okay. So combine everything now, which is also going to be quite messy, but we will do it. 1 plus f prime square to the power 1 by 2, 1 plus f prime square to the power 3 by 2. I'm going to take some common factors. First common factor is x dot. Okay, this is a common factor. I forgot to write. Yeah, this is x dot here as well, so I wrote it here. This is x dot divided by, I'm going to take 1 plus f prime square to the power 3 by 2 as a common factor. Or maybe before that, let me write the following so that it's more easy to see. This is equal to x dot f double prime j hat 1 plus f prime square to the power 1 by 2. I'm just writing the first term. the second term minus negative sign, and then I have the vector I hat f prime j hat multiplied by x dot f prime f double prime 1 plus f prime squared to the power 3 by 2. And typically, a word of caution, especially in intermediate dynamics, the problems that we solve are very large problems, right? So, which means that I will not probably get to the end of the problem by the end of the lecture, but we will come back and then complete the problem in the next lecture. I don't want to rush through some of these algebra and differentiations. Okay? Take some common factors. Get rid of all of these. F double prime is a common factor, x dot is a common factor. I'm going to take this as a common factor. So I'm going to have dt by dt is f double prime x dot all of this. I'm going to have j hat. I'm essentially multiplying the numerator and the denominator by this particular term. So if I do that, then I'm going to be ending up with 1 plus f prime squared. Okay, so this is to the power 1, this is to the power 3 by 2. If I bring this down below, then I end up getting to the power 1. This is just basic manipulation. Plus or minus f prime multiplied by I hat. This is one vector here. This is the whole thing. Then the next one is I hat plus f prime. Okay. Det by ds, dt is the following. X dot f double prime 1 plus f prime squared is about 3 by 2. Once again, this is just getting lost in the weeds. It is fine. You have to go through this to get to the problem, to get to the equation of motion. And then I take the terms in the numerator, multiply them all together. So I'm going to have j hat plus f prime square j hat. All I'm doing is taking j hat, multiplying it through, and I'm doing the same thing. F prime I hat, so minus f prime I hat. F prime times f prime is f prime square j hat. Obviously see. I can cancel those terms. Okay? And so I have, after all of this, dEt by dt. dEt by dt is now a much better looking 1 plus f prime square to the power 3 by 2. And then I'm going to have negative I hat times f prime. And plus j. This is dEt by dt. With your permission, I'm going to do the following. I'm going to erase this guy, okay? And I'm going to bring in ds by dt to the denominator of all of this here so that I can write kappa here. Okay, so So once again, what I'm doing is I'm going to get rid of this. This is dEt by dt, remember. We already have it there. So kappa En is all of this guy in the numerator. Divided by ds by dt, remember, which we already had obtained as x dot times 1 plus x prime square to the power 1 by. And this can be written much better as the following. X dot cancel off. Okay. This cancels off with that. I'm going to combine this 3 by 2 power and then 1 by 2 power. That becomes 3 by 2 plus 1 by 2, which is 4 by 2 or 2. So I end up getting kappa then is f double prime minus f prime I hat plus j hat by I'm going to write that result on this panel. Okay, that's the result that we have. Kappa En is f double prime minus f prime I hat plus j hat 1 plus f prime square. Yes,
So would this hold for all planar problems?
absolutely. Quite a powerful result actually. You take any planar curve, these equations hold true. Which begs the question, what exactly is kappa? We haven't found out what kappa is, right? So now we can do that. Now we can actually find the curvature of a planar curve. How to do that is by saying, okay, hey, this is a vector. This is also a vector. If they are both equal to each other, then their magnitudes have to be the same. Magnitude of the term on the left hand side is just kappa, because the magnitude of En is 1. Magnitude of the term on the right hand side, because I have these guys, these are all magnitudes, they remain the same, but I have to take the square root of the sum of the square of the components. Okay, so let me do that next. So magnitude of kappa En is kappa. Magnitude of the term on the left hand side, right hand side. By this magnitude is f double prime. Doesn't do much. Denominator doesn't do much, it's a magnitude already. Magnitude of a vector is the square root of the sum of the squares of its components. So this is going to be magnitude of f prime square, f prime, negative or positive doesn't make a difference to us, plus 1 to the power 1. You obviously see 2, factor of 2, factor of a half, that reduces to 3 by 2. So I have, this is equal to f double prime by 3 by 2. And this is a formula that I hope you've seen somewhere. The formula for the curvature of a planar curve. Typically when you do beam bending, you will start off with the curvature and then you will approximate it in many ways, right? So you'll see that here. curvature kappa is now f double prime by 3 by, because this term is the same as that term. It's a very standard formula. The inverse of the curvature is the radius of curvature, 1 by rho. Typically in strength of materials, you will assume that this df by dx is very small, so this quantity is ignored, so that your curvature is just the second derivative of the planar curve. That's your starting point typically in beam bending problems. Okay? So this is a very common formula. This is, in a way, we have actually derived the curvature of a planar curve. I have to make a point here. In our class, we treat curvature as a positive quantity, which means that if I look at this term f double prime, it could be positive or negative, right? Because it could be whatever it is. So for me, I want to take the absolute value. This is a positive quantity no matter what you do, because it's a square root quantity. So I'm going to end up with a positive value there. So in here, I'm going to take the absolute value of this. So that kappa is always positive. And so if I write my equation, kappa En times whatever that is, here's what I have to write. Kappa En, which is f double prime and all that, minus f prime I hat plus j hat by 1 plus f prime square. This is the equation that we had just derived. I'm going to substitute for kappa. And I'm going to say the following. F double prime is the absolute value of f double prime multiplied by the sine of f double prime, SIG. Okay, this makes sense, doesn't it? I can take any quantity and say that, okay, it's the absolute value of the quantity multiplied by whatever is the sign of that quantity, positive sign or negative sign. Substitute for kappa, substitute for f double prime in the last equation. You have the following now. Amplitude of f double prime, f prime square to the power 3 by 2, which is kappa, multiplied by En. Right hand side is f double prime, which is this quantity here. Absolute f double prime, sine f double prime. All of this by 1 plus f prime square whole square. And so we have now gotten rid of this pesky kappa creature, because every time I don't have to keep calculating that when I'm doing a transformation from the normal tangential to the Cartesian system. So I cancel this guy off, this is gone, they are both absolute values of the same quantity, so you can take them off. To the power 3 by 2, if it comes here, 2 minus 3 by 2 is 1 by 2. And so I end up with a very nice equation actually. So En, don't forget the sign of f double prime minus f prime I hat by j hat 1 plus f prime square to the power 1. And I'm going to replace the last equation here with that. I'm going to get rid of some of these things, just rewriting it while you write down what I have, of course. And all this is essentially in some ways an introduction to elemental differential geometry. So I take a surface and I perform vector calculus on the surface. And that is the nature of differential geometry. Okay? You either do differential geometry with respect to spatial variables. If you're doing problems in plasticity or elasticity, time doesn't play a role. Time independent problems. If you're doing problems in dynamics, there is no deformation, but time plays a role. So you have to include time derivatives. Okay. So what have we accomplished so far? After all this scintillating stuff on the board, we accomplished very little. We have accomplished only 2 formulas. Has not taken us any much further into the problem, but bear with it. Okay? So now I have the capability to transform for a planar curve, mind you, for a planar curve, not for a 3-dimensional curve. For a planar curve, we have the capability to transform between the tangential normal and the Cartesian system. And this is generic for all planar curves. So in your homework, you don't need to derive all of these again. Okay, you just make use of it. Alright, so now we go back to our problem. And we need to write the equation of motion, right? So which means we need the kinematic variables, we need the velocity, we need the acceleration and so on. So let's start off with that. I'm going to take a different track here. Okay. This is x, this is y, we know that. We know that the variable that defines the distance traveled is s of t. At any point on the trajectory, I have the tangential unit vector, right? That's going to be dt. What is the direction of the normal unit? By convention, because of the fact that we are assuming the curvature to be a positive quantity, the direction of the normal unit vector is always going to be pointing towards the center of curvature of the body, on the concave side of the body. Okay, this is by convention. Yes?
Is that what it means to have positive curvature?
Absolutely. Which is why we said that this is that's an absolute value. Absolutely. So in the direction of positive curve. Exactly. So in this case, if you want to draw what you call as oscillating circles or tangent circles, if I have a trajectory of this nature, then I draw tangent circles on the concave side of the trajectory, the positive side of the trajectory. So that's a circle there. That's a circle there. If I have to draw down this portion here, that's another circle there. These are called as the oscillating circles or the tangent circles. Okay? So they are tangent at any point that you desire to draw the direction of the normal unit vector. Right? So if that is the point I've chosen, then the normal unit vector is going to be towards the center of curvature on the positive side of the curvature. Likewise this way, likewise that way. You would have seen this in dynamics, right? ME 2030. This is the reason for doing all of those things. There, they would have just told you, okay, assume it to be this way. Now we've actually derived. Okay, so these are the tangent and the normal directions. So this is dn. This is ut. And we do the same thing for our problem as well. So the normal direction is going to be pointing inwards here. Perpendicular. The binormal direction is into the page. I'm not really worried about it because it does not play a role. Because of the fact that we have a planar curve, the torsion of the curve will be zero. Okay, and I'll have that as maybe I'll prove that as a by note in the lecture notes. It's not really something that we are wanting to spend time on. So this is what I have here so far. Kinematics. Let's set it up. If I want to write the velocity of the particle, respect to the fixed frame F1. Okay, F1 is this frame here. I can either say this is d by dt of r of t. Okay, this is p slash o, which we have already derived. Or I can say more easily, and I think I should derive this, but I'm not going to do it. This is fairly straightforward to think of. If I use the position, or if I use the distance traveled along the path as my variable of interest, what is the velocity of this particle at any instant in time? What is velocity? Magnitude of velocity, what is the magnitude of velocity?
Is it ds dt?
ds dt, s dot, right?
Yeah.
S dot, and it's always going to be pointing along the tangential direction. Okay, so we can write it this way. Or if you are in doubt, you can do the following. You can look at dr by dt, which we had written somewhere here. It's going to be x dot, and then I hat in whatever that is, plus prime j hat divided by 1 plus x prime square. That's it, right? Yeah, that's it. And you can do the following. You can substitute for I hat. You can substitute for j hat in terms of the tangential and the normal unit vectors, which you can do by using the transformation equations here. If I write et as a function of I and j and en as a function of I and j, I can do the inverse transformation as well. Okay? And you can do the substitution, and you'll end up seeing that the normal components will not play a role in the velocity. You'll end up usually getting s dot et. They are the same. So all you have to do is substitute for I hat in terms of en and et, j hat in terms of en and et, and it will end up giving you something that is common sense. Where s dot is related to x dot and so on. Okay? So something like that. So that's the velocity, that's the first kinematic variable. Now acceleration. So v slash o is s dot et. My degree of freedom is not s dot, my degree of freedom is x of t. So if I have to substitute, I can substitute for s dot and say that vp is all of those quantities. X dot 1 plus f prime square to the power 1 by 2. So that's the equation 1. Acceleration. This is with respect to the absolute frame acceleration. Is the rate of change of the velocity vector itself. So this is d by dt with respect to f1. If I know velocity, I can find the acceleration by differentiation. So I'm going to differentiate this term here. This is d by dt. S dot dt. All of this with respect to the fixed observer, so I'm not going to keep writing it again and again. The rate of change of the first term is s double dot plus h dot dEd. dEt by dt I can write as a follows, right? Then S dot remains as it is, okay? dEt by dt is dEt by ds times ds by dt. Chain rule once again. Two things that you will see used throughout this course: chain rule, product rule. By the end of the day, you'll get pretty tired of seeing it many times. But it's very important to see in the perspective of dynamics. ds by dt is s dot. What is this term here? Anybody? Yes.
So like the line going towards the center curve, the curvature.
Right. What's the line going towards the center of curvature? It is nothing but the normal direction. But you have to write it as a kappa times En. You see from the definition of the first Frenet-Serret formula, we said that dEt by ds is kappa times En. So I have your formula from undergraduate dynamics, S double dot Et, which is the tangential component of acceleration. And then I'm going to have S dot multiplied by ds by dt, which is S dot times S dot, which is S dot square. What a kappa En, because this term is kappa En. Tangential component of acceleration, the normal component of acceleration, you would have seen this as v square by rho or something. That's the terminology that you would have seen in 2030. Rho is inverse of kappa, which is the radius of curvature is rho. Okay. So for a straight line, the radius of curvature is almost infinite. One cannot define it. Curvature is 0 for a straight line. So if you have rectilinear motion, you are just going to have only tangential acceleration. Does this all bring back memories from dynamics? The things that you would have seen zooming past, but we are spending some time going through those basics, digging up those things, and then looking at the ideas. Okay. All right. Any questions so far?